Okay, so we are gradually ending our discussion of Riemann integral, and this is the last part where we are going to talk about Riemann integration. So, fundamental theorem of calculus in the Riemann approach. So, we are not going to prove anything here, but maybe one or two things we will prove which we can do fast. Otherwise, our aim would be to mention the theorem, and our aim would be then to illustrate what the result tells us. So, you have a function f which is in RAB, a bounded function, integrable on RAB. RAB means this is a set of all bounded function which is Riemann integrable on AB. So, you have this function f on RAB and you define a function capital F. So, you define a function f again from AB to R as fx is equal to integral a to x f of x dx. Now, we have spoken about this fundamental theorem when we had spoken about the whole thing in our in Riemann in the Newton's calculus, when Newton's integration theory, when we were speaking about integration, we had spoken about this theorem. So, what we have proved actually there, so that is why we are not repeating the proof here, right. So, what it says is the following: if f is continuous on AB, then if f is continuous on AB, then small f is continuous and capital F is differentiable of course. Right and left derivative is on the end point, there are these left and right derivatives, so that is assumed. So, f is differentiable, and because one might start asking what do you mean by differentiability in the closed interval. It is clear that f dash of A is f of A, which is clearly defined, and f dash of B is f of B, which is clearly defined. Of course, f dash in that sense, when f dash of A means the left derivative and f dash of B is the right derivative, that is all. So, that is what this theorem says, and we also gave you some warning of how to use this theorem, right. Now, if f is a continuous function, and so straight corollary is the following. So, if f from AB to R is continuous, this is also we had done, and where we introduced the idea of antiderivative basically. But there was a crux. I hope you remember the example which I had given. That was something very important that you need to keep in mind, that f from AB to R is continuous and f is equal to g dash, means f of x equal to g dash of x for some g, from AB to R. So, if this is there, then integral a to b f of x dx is equal to g of b minus g of a. So, you might be wondering how to prove this. So, is g the function g is the function which is f? No, that is something one has to be very careful of. G is not the f function. There f and g, capital F and g should differ by some constant. See, let me construct, for example, construct fx. So, never think that because of these, that capital F which was given, there must be this g. So, what does it say? By this previous theorem, it implies that f dash x is equal to f of x is equal to g dash of x. But if two functions have the same derivative, then they vary by a constant. So, basically the derivative of these two functions, the difference of f minus g, the derivative of that is 0. So, f minus g must be a constant. So, it simply means f of x is equal to gx plus c. So, there is no uniqueness of this capital F, that is something one has to be very, very careful. Of course, you know from here that if I put x equal to a, then f of a is nothing but 0. So, g minus of g a is equal to c, because if I put a here, f of a would become 0. So, it will be g of a plus c equal to 0. So, minus g a equal to c, and when I put x equal to b, then you have g of b. So, f of b would be equal to gb minus ga. But what is f of b? F of b is nothing but the integral. So, that is your result. One might simply think, oh, this is just simply think that, okay, what is this integral? Integral is nothing, integral from a to b f x dx is nothing, but you have to find some function g whose derivative is f, and then gb minus ga will give you the integral. But you have to be careful here, the definition of continuity is very, very important, that f is continuous is a very important thing. You cannot escape continuity at here. The reason is twofold, because I am going to give you an example of a bounded function which is not differentiable, is not continuous and hence not differentiable, but has an integral. So, integral does not mean that it is just the difference of two quantities gb minus ga. Find some function which it will, you have g dash x and you can do that. So, it is very simple, you take an example, say f x is equal to 0 when x is not equal to 1, equal to 1 when x is equal to 1. We had solved this problem, we have shown that this is integrable. So, once we have shown this to be integrable, then it is clear that this function is not continuous and not differentiable everywhere, but still integration is there, but you cannot write that integral as gb minus ga. So, continuity is a very important thing here, that is what I am trying to tell you. There is no way you can write it as gb minus ga. Of course, there are certain cases, for example, if you have gx equal to x cube by 3 and what f x is equal to x square, then f x is nothing but g dash x. And of course, that will simply tell you that a to b x square dx is x a cube. So, b cube by 3 minus a cube by 3. So, now by induction you will have the standard formula which you know about integrals, that is known to all, any kid who has done some calculus would know that this is so you can prove this simply by induction. But you have to be very careful here. N equal to minus 1 is not something which you are going to bother about. N not equal to minus 1. If n is equal to minus 1, this is undefined. So, if n is equal to minus 1, then if when n is equal to minus 1, we write this as integral a to b 1 by x dx. Now, nobody knows how to do anything about it. Of course, you say, oh, I have read integral 1 by x log x is log x, so log b by log a. So, of course, you can do that if a is strictly bigger than 0 and b is strictly bigger than 0. If not, so in general, not knowing what a and b is, it is not possible to say anything about this integral. So, this is something you have to be very, very careful about, that just by applying that formula blindly, you may not always get something. So, because here there could be a scenario where 0 is inside, it will be minus 1 to plus 1 1 by x dx and then that is it. So, you have a function which is not continuous, which is just blowing up. So, if you have 0 to 1 say, then also this function it is meaningless, but you have 1 to some t, then it is meaningful. So, you can understand, because this is nothing but the hyperbola, and you understand 1 to some t. So, the area is clearly defined, but if I here I have the area just keeps on increasing, because the function blows up as I go towards 0. So, these are the certain things you have to understand, that the arbitrary writing formula is not always fine. So, just if I know that f x is equal to g dash x and I write them as integral whatever be a and b, I do not care, I write it as g b minus g a is wrong. Lot of things have to be taken care before you actually apply the fundamental theorem of calculus. So, what we wrote is essentially the first fundamental theorem. Now, here we will go to something more. What we have just written this for continuous functions. What can be said if we are just concentrated on integrable functions, a bounded function which is Riemann integrable or whatever. So, if you take any integrable function and if f is equal to g dash, right, f is equal to g dash for some g, then for even for such functions integral a to b f x dx is g b minus g a. So, that is what I am going to write down. So, now we are going off from Newtonian thing into the standard Riemann framework, that it does not matter, we do not have to bother much about continuity, only integrability of the function is important, and only the fact. Now, you can say that f is a function, f is a, oh you might say, oh then might say is not f continuous, but no, f is the derivative of a function. Derivative of a function need not be continuous. Every function need not have a continuous derivative. A very pathological example, this x sine 1 by x when f x when x is not equal to 0 and 0 when x is equal to 0. Say you take the function x square sine 1 by x when x, so you take the function say f x x square sin 1 by x when x is not equal to 0 is equal to 0 when x is equal to 0. This is a differentiable function, but its derivative is not a continuous function. So, g is a differential function and its derivative is the function f, so it need not be continuous, but we are expecting that it is a bounded integrable function. So, even under that case, even if you do not know anything about the continuity of f itself, you can still have the mean value theorem, and that is why, that is where we differ from what we have studied earlier. That is exactly the point where we have moved, or we have made an advancement in the thinking from the Newtonian, the 16th century thing, 16th, 17th century thinking to the 19th century thinking. So, we push ourselves 200 years ahead by this just little change that, but you have to understand, you might say, "Arey kya, what is this, just change, continuity tha nahi hai." No, taking away continuity of function is a big deal in mathematics, and it makes a huge lot of difference, and that is why I am telling that this what we are now going to do and we are really going to prove is an important result. Second fundamental theorem of calculus, second FTC. Let f be element of RAB and further let f of x is equal to g dash x for all x in AB. Then integral a to b f x dx is equal to GB minus GA. So, this is actually a very important result. So, which we are now going to give a proof, or proof would be from Spivak. We are actually discussing this from the book by Spivak, so which I write it down again. So, it will be found in other places also, but I prefer writing, discussing it from Spivak where it is written in a proper, clean way. Okay. So, we will now start doing the proof of this, and with this, once we finish the proof of this, we can end this. I want to end this part. We are not going to go and work through the things, because we will see if we find time. So, we will give some 1 or 2 examples. So, okay. So, we will start the proof of this. Cut kijiye to. Though we prove this result, but I would like to tell you that this result is very pathological. It is not so easy to find functions f which are integrable, not continuous, but is a derivative of some other function. It may not be so easy. This could be one of the examples. So, okay. So, generically continuity of the functions are important. So, you might see what we do now is a very simple way of looking at the proofs. So, let me just try to do the whole thing in very simple way. So, you have the partition P, which is given the same way as n points with this is the point A and this is the point B. Right. So, now once we have this, what we can now do is that we take G and compute Gxi minus Gxi minus 1. So, because G is differentiable, so there is some xi I which is lying strictly between xi and xi minus 1. This is nothing but the mean value theorem of Lagrange that we have applied. So, what is g dash x? So, g dash xi I xi minus xi minus 1 is nothing but f of xi I xi minus xi minus 1, but f of xi I xi minus xi minus 1 is less than equal to mi, that is the supremum over this interval xi minus 1 and bigger than the infimum. So, what we are showing here is that if I do not even have, even if I have continuity of f, I need not use the continuity of f, I can only use the integrability of f, that's just the thing. So, once I have this, what I have mi xi minus xi minus 1 is less than equal to, now this is equal to this and this is equal to this. So, g of xi minus g of xi minus 1 ठीक है. So, if you sum them up from 1 to n, this will be a telescopic sum, it will give you GB minus GA. So, you will get LPF is less than equal to GB minus GA minus UPF. So, this is true for any partition P. So, supremum over all partition P in P LPF is less than equal to GB minus GA less than equal to infimum over all partitions in P LPF, sorry LFP I guess. Oh, I think I am making a mistake, this is a sign I am habituated to, but LFP. So, I was writing LFP throughout following Spivak's notation, sorry UFP. So, this is, but because the function is integrable, this is nothing but the integral and this is nothing but the integral by definition. That simply means that A to B. So, you see integrability is used, not the continuity of, even if that is continuity, we really do not require to use the continuity argument, when a continuity of f. There are other proofs where you can use the continuity of f, otherwise you do not require, but you see it simply comes out here, which simply means but continuity is thus a generic condition. It is really effective when you have a continuous function, it is not effective when the function is not continuous. So, we have already achieved something in the sense that we have covered a huge ground in calculus. By that it is no mean feat that we have done it together and a lot has been done. So, the course that you are learning, it is not a, even though it can be thought of as some basic course in one variable calculus, but it is really not just a basic course, because here I am not only tending to students who are just want to have extremely rudimentary knowledge, but I am also tending to the ambitious. So, that is something I made very clear when I gave the 2-minute introductory talk, that I am motivated by this title of Corner's book, The Calculus for the Ambitious. So, essentially that is what I also want to repeat, taking the leaf out of Corner's idea that this is a course for the ambitious, that you really want to know calculus much better than many other people. So, we will stop this lecture here, it is slightly shorter because the next lecture will be slightly longer, because we are going to introduce something very different and you would see that things which are not integrable by the definition of Riemann integration would actually become integrable when we use our approach of the Henstock-Kurzweil integral. So, thank you and we will be back in the next class.